Okay, so the final bit of this is this reaction spontaneity thing, which I was planning on teaching yesterday, but when I got to this point, I could see in your faces that you were kind of a bit done, so I just left it. Okay? So today, for the first 15 minutes of class, we're going to very quickly learn about this, and then you're going to finish all of those practice problems off. Or practice problems, that's what they're called, right? And then we might need help, I don't know. Let's see. So, do you remember when we were doing the equilibrium spontaneity rule? Not equilibrium, I mean electrochemistry spontaneity rule. Waterfall goes up, non-spontaneous. Waterfall goes down, spontaneous. Right? No problems. Except for here, we're at equilibrium. So both things are happening. Both ways are somewhat spontaneous. So you can't say non-spontaneous, because some of it is happening. So what you can say is this side is more spontaneous than that direction. This happens more than that happens. When you do the ice table, the E's at the bottom, those reactants or products will be more than those reactants or products. Okay, that's what this is about. And that is about the percent. 99% stays as a molecule, 1% just ionizes. Right? All of those things is what we're just about to do right now. So when you look at your data booklet table, this one, and you find your acids and bases, that's what we were doing yesterday, right? We were looking on this table and we were finding them all. If you find that they are, the acid that you pick is above the base that you pick for your strongest and strongest, your reaction will be greater than 50% products. What does that mean? That means your equilibrium arrows would look, I suppose, like this. More products. Oh. More, oh really? Come on. Please. More products and less reactants. A and B, C and D. Does that make sense?
Like above in the book?
Yeah, so in that data table, if I chose, or pardon me, not if I chose, but the species listed, and I looked them all up, and I found that one, I can't even see what I'm circling, but let's just pretend, and that one were reacting together. So this is the acid side, this is the base side, so this is giving a proton to that. Before, in Unit 2, we would have said, this is spontaneous, the waterfall's going down. Okay? And that still is true, but the problem is with an equilibrium, if A plus B, equilibrium arrow C plus D, this way is spontaneous, and that way is spontaneous. The rate of both things are happening at the same time, so they're both spontaneous. So saying spontaneous and non-spontaneous, you can't do that here, but it's the exact same concept. Okay? It's the exact same idea. So if this is the waterfall going this way, we would say you've got more of this way happening and less of that way happening. If you've got that acid reacting with that base, Unit 2 we would have said non-spontaneous, but Unit 4 we know both ways are happening. So, but it's not going to happen very much. So A and B aren't going to make very much C and D, and actually C and D are mostly going to make A and B. Okay? So if you think of this as formation and decomposition, I suppose, so if this was element hydrogen and carbon, and you're making, it's dangerous, oh, pardon me, it's dangerous for me to make up an equation here because I don't really know which way this equilibrium would lie. That's not mass space either. That's not mass space either. Compound A and compound B are making, or pardon me, element A and element B are making element C. Okay? Compound C. Element A and element B are making compound C. That's better. Okay. Let's say compound C is very, very stable. And the elements are like sodium, not very stable, and fluorine, not very stable, and you're making sodium fluoride. That's a transfer of electrons on acid base, but non-transfer protons. But anyway, so this would happen a lot, and the decomposition of that compound wouldn't happen very much if it's this over this. I'm kind of speaking gibberish now by this point, really, so I'm going to stop. Yep.
So then you would say that the reactants are very reactive because they want to form that compound?
You would say,
how would you say that in words?
You would say, there's quite a few different ways you could say it. So you could say, are you talking about this way? The acid's below the base? In my yellow example?
Yeah.
So in my yellow example, the acid was below the base. So you could say the reaction yields less than 50%.
Mm-hmm.
Or you could say it favors the reactants. Or you could say the concentration of the reactants would be greater than the concentration of the products. Everybody okay with that? Or you could say the K value. If the reactants are bigger than the products, then this must be bigger than this, and so the K value would be big, or small, I mean. So they could ask you kind of a variety of ways for the same concept about the waterfalls going uphill here, so therefore it's non-spontaneous, meaning it doesn't happen very much. Spontaneous a little bit. Okay? Spontaneous a lot, spontaneous a little bit. Yes?
Could you also say like the reaction goes to the left?
Favoring the
Shifts to the
reactants,
left?
so yes, the left. No,
Shifts to the left.
because you're not shifting the equilibrium. You're not imposing a system and causing it to shift. But you would say it lies to the left. Okay? Not shifts to the left, but lies to the left.
So this is different than
Or favors the left. Is that on here? Oh, yeah, it is. But favors reactants, favors the left. Pardon?
So this stuff, like when we're looking at these kinds of reactions, it's not the same as when we were talking about the shifts, like 2 days ago.
Correct. The shifts are different. Here's the equilibrium. Let's change something and see how it affects it. Remember the grass line, bump line. Versus this is just, there's the flask all by itself at equilibrium. Knowing where they are on your data booklet, can you tell me if you're going to have more reactants or more products in that flask? Okay? Okay, so in your practice problems, let's do question 8I together. What I find a 8I. What page was that on again, please? Somebody?
690.
690. Okay, so predict the direction of the following reactions and state whether the reactants or products are favored and give reasons to support your decision. So I'm going to go here and I'm going to have to zoom it up so I can at least read it. However, then it's chopped in half. And I need to find them on the periodic table, or I mean on the data booklet table. So can you find your things? Ammonium ion is somewhere down here. So we've got NH4, do we? NH4 plus and H2PO4 minus. Can you find that one?
Yeah.
H2PO4 minus. Now somebody else is going to find H2PO4 minus here. See how it's here as well?
Yeah.
Okay. How do I know to choose this one and not this one?
That's the base.
Because it's the base in that reaction. You've got the reaction of NH4 plus and H2PO4 minus, and you can see I'm transferring a proton from that to that. That's my acid, that's my base. So this is an acid in the acid column. This is the base in the base column. I don't need to look at that one in the acid column. And somebody else is going to say to me later on, but it's a stronger acid. Yeah, that's all. That's great. If you're right, it is a stronger acid than this, but it doesn't have anything to transfer its proton to. If you want to act, if you want it to act like an acid, if you want it to be an acid here, this would need to be a base. Can NH4 plus be a base? No. NH3 can be a base, but I don't have any of it yet. After the transfer, now I've got some NH3 there. And now that can be a base. But in the initial, do you remember that thing from Unit 2? You can only look at what you started with, not what you're forming. Do you remember making that mistake in Unit 2? Trying to find it on the wrong side? I'm like, no what? You haven't started with any of that. You haven't started with sodium, you started with sodium ion. Okay. So those are my two. This, in Unit 2, we would say is very non-spontaneous, wouldn't we? Yeah? Waterfall's going up. Non-spontaneous. So, but now, because we know some of it transfers, we can't say non-spontaneous. We will have to say only a tiny bit does that. Only a tiny bit of that protein is transferred. Essentially non-spontaneous. Okay? But most of it, the NH3 and the H3PO4, most of it is going to go this way. So a lot follows that pathway, and only a little follows that pathway. Everybody get that?
So you say
And by a lot, I mean a lot. You could say that a lot of different ways. So how have they asked it? Predict the direction of the following. So the direction is right or favoring the products.
Wait, isn't it the other way around?
Oh, sorry. Sorry. Let me go again. It's this way.
Yeah.
So thank you. Left favors the reactants. Thank you. I'm half asleep still this morning. And that's it. Predict the direction and state with reactants and products are favored. What if they asked us for percentage? The percentage would be less than 50% of it is going this way, the way we're reading it. Is going this way, the way we're reading it.
So when you say that, when it says like, predict the direction, like you just say left, you would say like there's just left, you don't want to put anything else that like goes to the left, or?
I don't like it saying predict the direction, because it doesn't really, it's going left and right.
Yeah,
it's going
that's why
more
I'm
left
confused. Yeah, okay,
than right.
okay.
So a better statement would be more left than right,
Okay.
or we say it lies to the left.
Okay.
Does that make sense? Yeah. Okay, so do number 2 on your own. Oh, and by the way, that kind of makes sense. H3PO4 is a pretty strong acid. It would make sense you'd have more of that being the acid than NH4 plus being an acid. If you've got all 4 things there. Okay, so do B on your own while I try to find them on my board. Okay, so I've got H2S here, and I've got water up here. The waterfall's going.
I'm just.
What's the matter?
Why do you use H2S?
It's just HS.
Oh, it's only HS? Thank you.
H chart is going on.
Okay. So, hold on.
And I think water would be an acid, but
I didn't read the question. Let me read the question. Water is transferring a proton, right? So water is the acid. So water and HS minus. HS minus. Okay, there we go. All right, and the waterfall is going.
But those are both on the same side. Water and
Nope.
no, but like they're on the same side of the reaction.
Yep, that's okay.
Okay.
That and that are reacting together.
Okay.
Just like in Unit 2, I had an oxidizing agent and a reducing agent on opposite sides. And they were reacting together. Okay? Shut your phone off. What's up my phone?
Is it mine? What's going on? Sorry.
Okay, so waterfall's going up here. So spontaneous or non-spontaneous? Craig? What would we have said in Unit 2 if the waterfall goes up? We would have said non-spontaneous. Okay? But now in the equilibrium unit, we know that we need to change that vocabulary into saying it's only a little bit of it happening. Only a little spontaneous. Just a little. So with the water and the HS minus, only a little is doing that, and most of it is going the other way, which is the H2S, oops, and what? OH minus. You know, think about this. Hold on, think. In actuality, you have all four things in your flask, right? Agreed? Mm-hmm. So this and this are reacting together more. That's what you just said to me. That's happening the most. Let's find those here and here. That way is spontaneous. That way is happening. Abby, put your phone away. That way is happening more.
So you could use the other side if you want.
So why is it happening more?
Because the other side's happening less.
Because the other side's happening less. Why though? Annalise, what did I just say? You asked a very good question.
Because the H2S is a stronger acid.
Because the H2S is a stronger acid than the other acid that's in our mix, which is that one. And so this happens more. This is a stronger base, so it happens. Oh, pardon me. This is a stronger base, so it happens more than this one reacting as a base.
So you could look at either side of the reaction.
Both sides are happening at the same time.
Okay.
You only choose one side to look at in order to talk about it, but you could explain it both ways because both things are happening.
Okay.
Yes.
Is this related to the ionization percentage of each acid on either side? And then the ionization
That is that 50% bit. That 50% bit is the ionization percentage if you're ionizing something. It's the percent yield if it's a reaction. Okay?
So you can look at
Yes.
If the products are favored in one of those reactions, would the percent be greater than 50%, or would it be like 99?
Well, you will never, the only way to do percentage is if you do an ice table, you find out equilibrium, it's this concentration. I could have had a maximum of that concentration doing normal stoichiometry, and therefore my percent yield is what I actually got divided by what I totally possibly could have got times 100. Remember that? That was a few days ago. Yeah. Okay, so it's not that hard. You just need to do it and not be texting while you're doing it, and you'll get your head around it. Promise. So have a go at C now. And question, have you finished question 10? Hands up if you finished question 10. Half of you. Okay. So do 10 is more important than 9. So do 8, 10, and then 9. All right? Those of you that have already done 10, you can do 9.